request Mr. Dhruva Shaw to please present us.
Jai Hind, respected jury members and the audience sitting here. I am Dhruv Shah and I am pleased to present our collaborative work at CreativeNet. We have been developing a mind control bionic arm which incorporates the tactile feedback, and this project is a collaboration with the contributions from Aditrabha Sengupta and Bhavya Chaudhary in the domain of biotechnology, and Jai Baswaraj Kaple in the domain of electronics and communication, and it's under guidance of Dr. Ramdeep, and I am leading this project, and I am leading this project in the aspects of robotics and automation, and here I will be discussing the results and findings of this project. So here we are introducing a cost-effective bionic arm design to restore the normal hand function in the amputees or individual with paralysis. So this design actually incorporates a touch sensor in the gripper, which actually enhance the user safety and the dexterity. Our main goal is simple, that we have to replicate a natural arm design, so that natural arm design and all the complex movement with the sensory feedbacks. In layman terms, you can say that imagine a prosthetic arm which you can control with your thoughts, and you are wearing a headband and you are just thinking, okay, that we have to pick up this project, a thing, and your arm would move and you can sense everything. Our proposed arm design prioritize like 3 functionalities: integrated sensory feedback, mind control potential, and one of the most important thing, non-invasive nature. So at first I'll explain you the flow chart, like how we are doing our thing. So first we'll acquire the data from the patient, and then we would do the pre-processing, and from there we would extract the features, then it would go to the AI model, it would do a classification, and from there it would go to like further data analysis, because since it's a robotic arm, it needs to be under closed loop system. So we need to send back data to the input again for the further rectification and thing, and then arm would do its thing. So the model was trained on publicly available EEG dataset. It was not a single dataset, it was 2-3 dataset combined together. Initially the dataset encompassed of 60 volunteers with 8 different activities, and all volunteers contributed to 8,684 seconds EEG recording, and it was collected using 16 dry EEG electrodes arranged in 10 by 10 international system. This is the 10 by 10 the placement of the electrodes. So monopolar configuration was used with the potential of each electrodes measured relative to the neutral electrode placed on both of the earlobes. It is used as a ground reference. So the EEG signal was sampled at 125 Hz, and it was filtered using a bandpass filter of 5 to 50 Hz, and then using a notch filter operating at 60 Hz. Okay. So now, before I move on with this presentation, I have to make it clear of the scope of this presentation. Like till now, what all work we have done? The work we have done is develop the AI model, which was the first necessary. Then we have designed a robotic arm in the virtual environment, and we have done the virtual environment simulation. That's it. Still now, touch thing hasn't been developed yet. It is just been theorized. Like in future we'll develop it. Okay, so now let's come to the data pre-processing part. The data set was in the CSV file format, and it contained 16 columns, each column representing a single channel data. So and it was recorded corresponding to 8 distinct activities, and the activities are follows: baseline with eyes open, closing left hand, closing right hand, dorsal flexion of left foot, plantar flexion of left foot, dorsal flexion of right foot, plantar flexion of right foot, and then the resting between each task. And throughout the presentation, we would be representing with their short forms as it's being shown below. So in the pre-processing part, we first split the channels into individual CSV files. Like since I told you there were different data set combined together, so actual number of data which we had was 74,441. After we split it up, it had gone up to 11,91,056 CSV files. After that, then we have converted into audio signals in the .wav format. So after converting into audio signals, you can essentially hear your brain signals, and it was all done using Python, the all pre-processing workflow. So now the audio files were imported into MATLAB using the audio data store feature, and then the data set was divided into training, validation and testing, each allocating like 70, 20 and 10% respectively. After that, after importing, MEL spectrograms were extracted from the audio files. It basically provides a time frequency representation in an image format, and it was done using the YAMNet preprocess function of the MATLAB. Now let's come to the transfer learning with YAMNet. YAMNet is basically a deep neural network model with 86 layers. It usually had 521 classification things, which was YAMNet was utilized as a base model. And then we froze the initial layers of YAMNet, and then a new classification layer was added so that we can perform our own 8 classification task. Then the model was trained using the initial learning rate of 0.0003, and it was on the exponential learning rate schedule. Mini batches sample of 128 was taken for training, and the model was validated after every 651 iteration. So that one is the confusion matrix. So here is the results. From the results we can see that we have an accuracy of 80.64%, which means YAMNet did pretty well job. And for the note, training of the model took around 12 hours, and the process was split into CPU and GPU threads. So this is the Simulink testing that we have done. So this is basically the whole system, and this is the subsystem of this. Like since I told you we are connecting 16 channel data, so this is the 16 channel, and that one is the 1 channel data collection system. So basically we are collecting the analog data, then we are passing it to notch filter operating at 60 Hz, and while collecting the analog data, it is being sampled with ADC at 125 Hz. Then this is the band pass filter operating at 5 to 50 Hz. Then we are passing it to YAMNet preprocess block where MEL spectrogram is extracted, and from there we are transferring it to our own transferred learning model that we have done with YAMNet, and then the classification is being done. And after this, every classification, like what all the output is being given, it is being collected, then a mode operation is being performed. Whichever frequency is highest, that's the output. So at last, so the conclusion and future work: to enhance the accuracy and performance of mind control bionic arm with sense of touch, we propose some following refinements that we are intended to do in future, like feature augmentation. Since right now we are only depending on the MEL spectrograms, so we are thinking to incorporate additional features like labeling of delta, theta, beta and gamma waves in these signals, and then also further signal processing metrics like SNR, bandwidth, mean frequency and occupied, so that we could incorporate more features and our accuracy is more. And apart from that, we are planning to perform an ensemble learning based on the signal processing metrics like SNR, bandwidth, so that we could identify we could take in more number of features in consideration. After that, of course, we need to build the hardware, the EEG collection hardware, and perform it on a live data. And after that, of course, the tactile feedback development, which is the main important thing. So right now, the thing which we have theorized for the tactile feedback development, that we intend to put a capacitive touch-based thing on whole of the arm, so that whatever touches the arm with the pressure or force, that signal sends back to the nerve or the brain. So thank you. This concludes my presentation. We are confident enough that we would soon finish this project, and the product would be soon launched in market for the general mass, making a significant impact in the life of amputees. You can please scan this QR code if you wish to know more about the project. It would redirect you to short.dhruvshort.in/mcba. Jain, now I'm happy to answer any further questions you may have.
Yes. You have like in result, you have sensitivity is equal to 0, what can be measured?
Where?
You have a sensitivity very class or particular class.
Okay, so like sensitivity value for particular class, it's being not performed, like it's being taken from these three things. In MATLAB there is a function known as stats of measure, which calculate all these values from the confusion matrix. We are only taking the accuracy thing. It's still in the development stage. It's still not has been finalized yet.
But you evaluate your model, you take all the measures, sensitivity, F1 score.
F1 score is there. This one, F measure.
I'm just saying, like for that classes, the sensitivity is very low. It should be improved.
Yeah, right now it's very low, but we have to still improve. I'm telling you, it's still in the development stage. It's still not finalized.
And like, what is need of converting to audio file? Like directly we can use EEG format.